It was remarked that long period motions at sites close to the fault are most sensitive to nearby slip on the fault. And there's concern that when we, it's a point that Tom made, there's concern that when we define everything in terms of magnitude, this may oversimplify the problem. And so at the meeting, there were several suggestions. One was to check the long period motions, pseudospectral displacement against fault slip. We could also check the static displacement against fault slip and compare the simulated motions with the GMPEs for spectral displacement. I guess one of the other questions is if you're doing a simulation at a particular site for a long fault, are the motions at that one site representative of the range of motions that you'd expect over the entire length of the fault given a heterogeneous slip distribution? So that's, I think that's the question that this talk is going to address. And to look at this issue, we went back to the broadband platform simulations and only looked at one event so far. The lander simulation case, there are 50 realizations. This is showing the location of the lander's fault scenario, and there's the Lucerne station, the Joshua Tree station. So these are two stations that are within about, say, six or 7 kilometers of the fault, opposite ends of the fault. Now these were the broadband platform validation exercises, so they have the same hypocenter. The hypocenter wasn't randomized in this case, so there is a directivity effect. Okay, so this is an example of one of the slip distributions from a Graves and Petarca San Diego State University simulation. I didn't look at XSIM because there's not a slip distribution to look at, and I'm only going to show results for Graves and Petarca because we're looking at pseudospectral displacement, and the periods are long enough that the two methods are producing the same result, or at least very, very similar results. So on this slip distribution, it's showing the position of Lucerne and Joshua Tree, one particular realization. And so at the meeting last time, rightfully it was mentioned that at long periods, the motions are going to be controlled by the local fault slip. And it was the discussion centered around the nearest surface slip. Now there's other measures that we can think about. I did look at surface slip, and there is a correlation, but it's not a very strong correlation. And I think the reason for that is simply that's just the way we looked at it, it's just a point observation of it's the closest fault slip. So to get around that, and that's really not the slip that we're interested in. What we're interested in is the most relevant slip. And the way that you can look at that is by performing a weighted average of the slip in which the weight function is the product of a radiation pattern term and the geometrical spreading. So you can think of it as a radiation sensitivity function that can be computed at every point on the fault for a given station location. And so for the slip distribution, same slip distribution in the top, in the figure below, it's plotting the fault parallel sensitivity. It's fault parallel sensitivity function. So this plot scales from 1 to small negative numbers. And for fault parallel sensitivity, there's going to be, it's dominated by one lobe that is for that portion of the fault that's closest to the station. The way this is computed is to first compute the SH radiation patterns, the SV radiation patterns, and then project into the fault parallel and fault normal components. And I've already said this. So we compute the inverse distance scaling at all points on the fault, and then it's the product that's plotted here. Okay, so this number from 0 to 1 in this color scale is the weight that can be applied to the slip. So what this is saying then is for a station that's located right here, let's say I take a level of 1/10, 0.1, then the part of the fault that that station is most sensitive to, in terms of fault parallel sensitivity, would be roughly this area here. Okay, so it is dominated by the near surface slip, but it's averaged spatially over the fault. And the width of this function is going to depend on the distance to the fault. Obviously, if the station's further away, then this opens up. If it's closer, it really collapses down. So that's the fault parallel sensitivity. You can compute the fault normal sensitivity as well. This one, remember, the computation is for the SH radiation pattern and the SV radiation pattern, and it's projected into the fault normal. So there's actually components of both, but this is really dominated by the SV term. Here the functions range from 0 to 2.5, and you see 4 lobes, but this is actually the spatial representation of the 2 lobe for the SV radiation pattern. Whereas for the fault parallel case, it's dominated by the 1 lobe radiation pattern. Okay, so that's the weight function. And then, so then the other question is, well, suppose we have a station here, maybe Lucerne's right here, this is our fault, and we can compute 50 realizations of the slip distribution. We can compute the time histories and the spectral parameters. And then the question is, well, are those long period motions representative of the range of long period motions that one might expect over the entire length of the fault? Okay, so what I did is I put some fictitious stations in here and computed the same parameter. And this is showing the distribution for the 13 stations by 50 realizations for surface fault slip. This is the closest surface, the closest point on the surface only. And so we have a lot of very small values near the station, and there's a fairly wide tail out to just about 6 meters of surface slip. And so that's for all 13 stations. And then this is comparing the same with the distribution at Lucerne. Okay, so that obviously there's many fewer points, but basically the Lucerne site with the 50 realizations is capturing the distribution of fault slip over the entire length of the fault through the 50 realizations. Okay, so then we can look at the simulated time histories. These have been rotated into fault parallel and fault normal components, integrated to displacement. And this illustrates, as Rob pointed out, that the Green's functions are complete solutions to the elastodynamic equations of motion. So there's intermediate and near field terms or static offsets in these time histories. Okay, so one measure that was suggested that we look at is peak displacement, and then another that I thought would be interesting to look at is a static offset. They're very similar, obviously, on the fault parallel component, on the fault normal component, they're a little bit different. Okay, so this is a plot now that's showing on the x-axis 1/2 of the nearest surface fault slip, 0 to, I don't know, about 230 centimeters or so. And this is showing the fault parallel static ground motion. And what you see in this is that there is a positive correlation, but the dispersion is quite large. And in particular, for nearest surface slip of 0, we have probably more than a factor of, more than a factor of 2 at least in the static displacement on the fault parallel component. Okay, so we saw correlations there, but they weren't very dramatic. So then we go to the next calculation, which is using the radiation pattern geometrical spreading weighted average. And this is showing the distribution of that average slip estimate for the 13 stations by 50 simulations. And so here we have a peak of about 150 centimeters. And could do a normal distribution test on it that looks somewhat normal, not quite normal, but it is what it is. And so then this is comparing the same against the distribution that you get at the Lucerne site. And the point here is just that the slip values measured in this way at Lucerne are within the distribution that you get considering the 13 stations that are distributed over the entire length of the fault. And when you use that as your fault slip measure, then you get a very strong correlation. Not really surprising in the sense that it's really, here we're looking at fault parallel static ground motion, and we're looking at a radiation geo-weighted average that's strongly fault parallel, that's dominated by the fault parallel component. It's dominated by the SH radiation pattern first, and then projected into those two components. It's dominated in the fault parallel component. So there's a relationship between fault slip in this relatively small area of the fault closest to the station and the static ground motion. Okay, so then we can look at this is peak ground displacement on the y-axis, fault normal. This is the fault normal ground displacement. And the x-axis is the same measure of fault slip. And here we see a positive correlation, but the dispersion is larger. And this isn't really surprising because on the fault normal component, there's a combination of, the contribution of a static term, but there's also going to be contributions from other points on the fault, directivity, for example, propagation of surface waves, body waves. The complexity of the wave field is going to be contributing strongly on the fault normal component at this distance from the fault. When we go to fault parallel peak displacement, again, the same fault measure, you can see that it really tightens up a lot, and there's a strong correlation between the peak displacement on the fault parallel component and this weighted average measure. Okay, and this is just showing the vector magnitude of the two components. So a strong correlation there. All right, so the next part of it was, well, let's look at the pseudospectral displacement. And what I wanted to do, since I did the calculation in terms of fault parallel and fault normal, I wanted, rather than use ROT-D50, which basically could have different combinations for different periods, I wanted to use the two horizontal components as computed, and not run into a case where the combination is different for different periods. So what this is showing now is the geometric mean of PSD for these simulations in the pluses. Okay, so centimeters here, increasing period to the right. The simulations go out to a period of 20 seconds. And what's plotted on this is the geometric mean of the site-corrected Lucerne data. Okay, so it's falling within the distribution of the simulations very nicely. What I've done is I've defined regions to look at the spectral displacement: 1 to 3 seconds, 3 to 7 seconds, which is near the peak of this function, and then greater than 13 seconds, which is where it gets down to the long period asymptote. Okay, so those are the data. And this is comparing PSD 1 to 3 seconds against this same measure. And you can see that there's a positive correlation there. 3 to 7 seconds and greater than 13 seconds. And so one of the things you see is that there's more dispersion in the PSD estimates of displacement than direct measures of peak displacement or static displacement. But they are correlated. And so the correlation is telling us that at other places on the fault, given different slip distributions, that we should be able to recover the long period response. It also suggests that we're not, if we're looking only at Lucerne, we're not missing anything with the 50 realizations. If we only had 2 realizations, then we most likely would be missing something. I don't know if we had 10. If we have 50, it looks like we're capturing the sort of variability that is present in the description of the source, which, as Rob has developed, is rooted in the Mayan-Barossa work. Okay, so that was all Lucerne Valley. This is Joshua Tree. Again, comparing fault parallel displacement, fault normal displacement. This station is near the end of the fault. There's components of static on both horizontal components, static displacement on both horizontal components. And comparing with 1/2 of the nearest surface fault slip, here you can see again about these are all values of 0 at the closest point, about a factor of 2 variation, and really no particular correlation in the simulations here. When you go to the radiation pattern weighted average, then there's a strong correlation, and the slope is negative because we're on the other side of the fault, and this is a right lateral fault. So the Lucerne side is moving in a different direction than the Joshua Tree side. That's all that means. Okay, so then looking at peak fault normal ground displacement, strong correlation for these with this slip measure, and fault parallel displacement. I would argue that it's, the comparison between fault normal and fault parallel are actually very similar here. That's because there's more of a mixture due to the location of this particular site at the end of the fault, near the end of the fault. And the last series of slides, I have a feeling this went by pretty fast. Hopefully not too fast, but we'll see by the questions. So the last 2 slides here are showing the pseudospectral displacement plotted in a log-log scale, increasing period to the right. The pluses again are showing the simulation results. This thick red line here is the geometric mean of the observation at Lucerne corrected for site, and I've plotted on here 5 of the GMPEs. And there's really a very good level of agreement out to about 10 seconds period. And so that was for Lucerne, and the same for Joshua Tree. This curve here that's plotting below the simulations is the observation, geometric mean, the observation site, and then it's within the distribution of the simulations at longer period. And here the GMPEs are plotting pretty close to the center of the distribution of the simulations. So this is showing at long periods in terms of spectral displacement. There's correlation between fault slip and also the GMPEs with the long period simulation results. So I think that's quite good. So to summarize, the static displacement, peak displacement, and long period PSD all correlate with spatially averaged fault slip. The weighted average, just to remind, was the fault slip computed using weights based on the fault parallel and fault normal radiation patterns with geometrical spreading. I used far field geometrical spreading. One could argue that you might want to use a combination of intermediate field and far field. I don't think the results would change very much by doing that. If you used the near field, then it would basically collapse 1 over r squared. If you use 1 over r squared, then it would collapse that region of slip sensitivity on the fault down to smaller area. And the results indicate that PSD from the GMPs are consistent with the simulations at long periods. So what this is telling me is that that we're not to address.
So when I look at the records that came off the hanging wall from the Chi-Chi earthquake, where we had 8 meters of displacement and 3.5 meters per second, and I look at what it would do to tall, flexible buildings.
Tom, can you put that a little closer?
I don't think there's a building on the planet that would withstand and survive that kind of ground motion, and a flexible one. And would that kind of motion show up in this analysis?
I think so. The Chi-Chi was 7.6.
Yeah, 7.6, 7.7. So.
Yeah. So here, here the maximum slip in the model is about maybe just a little bit less than 6 meters. So the 7.6 would have a larger maximum, larger average. So I think the analysis would capture that.
So when
the question is I think the question that you brought up earlier today is whether or not the models that are used to produce the source kinematics in the first place is capturing the extreme cases that we have some examples of. And that's a different question. I guess, but related to that, and I think an interesting one would be if you have a very large slip, let's say for a magnitude 7.3 Landers earthquake, and then there was a section of the fault that, for one reason or the other, had twice the slip of other 7.3s that built up the database. The question is, how important would that be in the context of its spatial average? If it was just one point, it would obviously be very important if you're very close to that point. If you're several kilometers away, then I think you would need to have large slip that had a wavelength or a scale length that was probably comparable to the distance from the fault.
I don't know how related this is to our nuclear problem, but lately I've seen examples. The one that really upset me was when Caltrans talked about the new East Bay Bridge. They said, well, it's good for 1,500-year ground motions. And all I could think was, do we really understand long period ground motions at 1,500 years that we could come close to making those kinds of statements? And I'm not quite sure what to conclude, except that I didn't feel that our science is anywhere close to being able to do that.
Well, as far as the simulations go, that's instrumental era earthquakes, and those earthquakes that have some reasonable estimate of the finite fault process, and that's a very small sample considering those sorts of recurrence intervals.
We are talking about an earthquake, let's say that's 1 in 200 years on the San Andreas for a big magnitude. So now 1,500 is a 1 in 7 or a 1 in 8 type of a ground motion. Then you're not so far, going down the distribution. Yeah, I think we know ground motions that are 1 standard deviation, and that's really all you have to do to get to 1,500 years. It's when you're going to go to 10 to the minus 4, 10 to the minus 5. Now you're pushing up to 2 sigmas and so forth, that you really start to get into the questions of it. But you do have to take out the return period or the recurrence interval of the earthquake to think about how rare the ground motion that we're talking about. Other questions or comments on this part of the? I was encouraged to see. I was expecting actually more disagreement between the.
I expect to see more too, based on the validation. The departures at longer periods.
They seem to be
this is just focusing on 2 particular records. Maybe 2 records that work pretty well.